Hello, this is Professor Gibson. Welcome to a video about Chapter 11, Section 6 on the normal distribution. This is an introduction to the normal distribution. Starts with a little story from our author or a thing he set up to try to help explain a little bit about the normal distribution. If you grew up anywhere near maple trees, you're probably familiar with the seed pods they drop by the thousands in the spring. Like almost all living things, the individual pods vary in size On any given tree, there's a typical size with some pods bigger and some smaller. On a beautiful spring day, I gathered 100 pods from the maple in my backyard, measured each, then grouped them according to their length. The smallest was 42 millimeters, the largest was 59, and in the photo they're grouped according to classes. 42 to 43 millimeters. In other words, what he did is he grouped them according to classes, each class kind of 2 millimeters, right? 42 to 43, 44 to 45, etc. All right, so let's look at what he made. Oh, my thing is, come on. All right, there's the next picture. So here's the seed pods. And so right on the smallest seed pods here are the ones from 42 to 43 millimeters. There's only two of them. The biggest seed pod was somewhere in the, I think he said it was 58 to 59. There's only one. And so notice here, as you move towards the middle, right? So here's the middle size, right? It's probably more or less the average of here. It's probably right in here. And there's more of those than there are of anything else, right? And then the further away you get from the average in either direction, the fewer you've got. In fact, if this was a perfect normal distribution, these would all be, each of these categories would have exactly the same number of seed pods in them. Now, in real life, they're pretty much never perfect, okay? But they're often relatively close like this one. All right, so that's what a normal distribution looks like. The distribution, formally the mathematical thing, would look more like it would, it's what's called a bell-shaped curve, like that, right? So the x-axis might be about right here, right? Actually, the curve goes on kind of infinitely in both directions, like this one and the other way. It gets closer, and the further away you get from zero, the closer it gets to zero. Further away you get from the middle here, rather, the closer that gets to zero. Now, the other thing I want to say here is, let's say we're really going to be talking about probability, okay? So let's say you wanted to know the probability that you randomly picked a seed pod and it was less than this size right here. Well, the way the normal distribution works is, what that would mean then is this area and this right here, that is the probability of being less than this right here, okay? If you wanted to know what's the probability of being bigger than this spot right here, right? Then this area right here, out to the right, all this area under the curve here, equals that probability. You want the probability being between this number and this number? Well, then it'd be the area of this whole kind of box sort of thing underneath this curve. That would be the probability of being between this number and this number. Okay. It's called the normal distribution, by the way, mainly because it's just so common. It's easily the most common. There are all kinds of things that are distributed according to this pattern, this normal distribution. Sizes of a wide variety of individuals. Like in this one up here, we had sizes of seed pods, sizes of people, sizes of animals, sizes of all sorts of things in nature. IQ scores tend to be normally distributed. Lifespans of batteries tend to be normally distributed. If you, I mean, there's just all kinds of stuff, okay? Both biological, chemical, all kinds of things show up. It's easily the most, now there's a lot of stuff that's not normal too, but it's by far the most common. That's why they call it the normal. All right, so let's talk about some properties of a normal distribution. First, the mean is always in the middle, okay? Second, the distribution is symmetric about the mean. This means the graph to the right of the mean is a mirror image of the graph to the left. Okay. Third, the graph shows the probability of randomly selecting any data value in a data set that follows the normal pattern. The area under the curve equals the probability. We already talked about that one. The key to calculating the probabilities is to first calculate how many standard deviations the values in question are from the mean. This is the key, and we'll talk about this more in a couple minutes. something called a z-score. All right. Here's the formula for it. If I write it out to the side, it looks more like, so z equals, if x is the data value, so it's the data value minus the mean divided by the standard deviation. Okay, that's your z-score. And what it gives you, this is the number of standard deviations the data value is away from the mean. This is the key, right? Remember, I said a moment ago that the first step is to figure out how many standard deviations we are away from the mean. So we calculate the z, and that's what z is. It's the number of standard deviations away from the mean with a little bit of extra, because z is positive when the data value is above the mean and negative when the data value is below. All right, so to calculate the z, it tells you the number of standard deviations away from the mean, and by looking at the sign, it tells you whether it's above or below. One other little comment about probability is that remember, probability is always a number from 0 to 1. We're going to use this, okay? An event with 0 probability will never happen, and an event with a probability of 1 absolutely will happen. So kind of going along with this, let's say the probability of some particular event, I'm just going to call this event E1. Let's say the probability that E1 happens is 0.65, right? It's fairly likely, 65% chance. What's the probability that E1 doesn't happen? What's the probability it doesn't happen? Well, since all probability adds up to 1, the probability it doesn't happen, we'll just do 1 minus that's the complement. 1 minus 0.65 would be 0.35. Okay. All right, so let's look at something else. Let's look at a few other things here. I'm going to just draw the graphs for these. We're not really going to calculate them. So if you get asked, what's the probability x is less than 0? A lot of times they'll ask, especially in the beginning questions, they'll ask what, if the area is less than 0. What is the area to the left of 0? 0 is the way they'll word it. Instead of saying a probability being less than 0, they'll ask what's the probability of being the area to the left. Okay, now remember, the area is the probability, right? So like the area to the left of this, right? That was the probability of being less than that point, right? Same thing with the 0. So when they ask you, what's the area to the left of 0, they mean what's the probability of being less than 0. And if you think about it, if you just draw a normal distribution, okay. All right, now once we're down to the level of z-scores and we're just counting standard deviations, it kind of changes things a little bit, because like the seed pods, 0 wasn't in the middle, the mean's always in the middle. But once we're down to the level, once you've converted it to a z-score over here, then what happens is z is always in the middle. I'm sorry, 0 is always in the middle. Well, if 0 is in the middle, guess what the probability of being less than 0 is? It's 0.5. Okay? All right. So this would be like this right here, right? What about the probability of being less than 0.35? Well, if we draw the basic graph again, okay? Here's 0, so 0.35 might be like something right here, right? So the probability of being less than 0.35 would be all this area here, all this area under the curve to the left of 0.35, right? Again, they're going to say area to the left in the beginning questions. Well, how are we going to do that? Well, what we're going to do is we're going to have a table that's going to show us how to do that. Okay? All right. Similarly, right, area greater. Okay. We do have some more time. So let's go ahead and look this up. Now what's going to happen is there's a table. Actually, in every question, they're going to give you a link to a different version of this table. I strongly recommend you use the table I've given you. Okay, the table is in the course content area. Go to the course content area in Blackboard. All right, you'll see now up near the top is a thing that says normal table or normal distribution probabilities, something, one of those. And you're going to open that up. Okay, here's what it is. It is it's a 2-page document. Okay, the first page looks like this. If you look at the top, it's got a little normal curve. And what happens is you look up the z-score, and it tells you the probability of being less than that. Like you see, this first one here is a minus 3.4, and then this is 0.09. Let's go over to 0.07. So minus 3.4, the way you read this is a minus 3.47. And then this 0.0003, this is the probability of being less than minus 3.47, okay? So a randomly selected data value, the probability it's more than 3.47 standard deviations below the mean is 0.0003. Remember, minus means below. You know the probability of randomly picking a value that has a z-score of less than 2.0? Well, here's minus 2.0. And if you look all the way over to the right, the column to the top is 0, 0. So minus 2.00. The probability of being less than that is 0.0228. Okay, now what's happening is, so the first page of the table we were just looking at has values that have negative z-scores, right? Negative, in other words, the number of standard for points and a certain number of standard deviations below the mean. The second page is pretty much the same thing, except it has positive z-scores. And the other thing is, I guess because it's positive instead of negative, the order of the numbers at the top reverses. Like you see, the 0.00 is in the first column instead of the last column, right? So you want to know the probability of randomly selecting something less than 1.55, say. So let's go 1.5, and then go over here to the right until we get underneath the 0.5. So there's 1.55. So the probability of being randomly selecting something that's less than 1.55 is 0.9394. And remember, some of the questions would say, what's the area to the left of 1.55? Okay? Now, the table always tells you the probability of being to the left, which is the same as probability of less than. What about greater than? Well, when they want to know a greater than, sometimes they'll say greater than, but a lot of times they'll say, what's the area to the right? Okay? If we were going to draw a picture, right, the area to the right, 0, 1 is going to be like out here, right? So it's going to be this area here. This would be the probability now. It's the area to the right. It's the probability of being bigger than 1. I'm sorry, I did minus 1 here, didn't I? All right, so bigger than minus 1, I'll just redraw it. So minus 1 will be like here. Bigger than that would be this area out here, right? Okay, this area would be the same thing as the probability of being bigger than minus 1. So how are we going to do this? Well, first, let's go look up in the table. The table is going to give us this area, this probability here being less than minus 1. So we'll go back in and look up minus 1. Minus 1.0 is, I think it's all the way to the right. Let's double check that. Yes, 1.0 is all the way to the right, 1.00. So minus 1.0, right? And then all the way to the right for 1.00, 0.1587. Okay, so this probability here being to the left of is 0.1587. So remember, now we're going to use our total probability thing in our complement, right? The complement of that, right? Anything that's, if its probability of being less than that is 0.1587, and the probability of being greater than that is 1 minus 0.1587 equals 0.8413. Okay? That is it for this one. Hopefully you find that helpful.